Right. At the moment, we are going to discuss different types of functions, like the ones you have decided to, after the linear functions, the parabola and hyperbola. Next one is the exponential function. Now, I'm going to use an example here. I'm using the example because the example offers itself to make me, according to me, to make people easily understand exponential functions. Now, what am I talking about here? I'll take an experiment which I did in biology when I was at school. Like, for example, this is not an experiment I did. Some theory which was given to me in biology is that the basic unit of life is a cell, like a cell as in C-E-L-L. That's the basic or the smallest living thing. So the cells multiply, maybe to make tissues, and then you get a body of person growth. But the problem with the cells, they don't multiply, they reproduce themselves. There's no mother cell, there's no father cell. What happens? This is both mother and father cell. One. What happens? This, first of all, this has got a life cycle. Can be one day, can be maybe it's any other time. But let's say here, we're going to assume that it's got a lifetime of what? One day. Isn't it? So they say now, this is the initial day. We number the initial day 0. Day 0. We start counting. So after one day, the cell would have grown through its life cycle, and it must multiply. And what happens? If it goes through multiply, it actually grows to a certain size and shape in a certain way. The nucleus, this thing inside here, also shapes in a certain way until it divides into two, and it cuts here. Once it cuts there, the membrane also, the outside skin, also joins and produces two cells. Sounds like a biology class, né? Where is mathematics there? So let's see. Now what happens now? At the end of one day time period, there will be two cells. I'm just drawing them small. They are of the same size. I'm just drawing them small so that I can have more space on my board, isn't it? So another day, it will be the second day. This one will get us two cells. And this one would deliver us two cells. We suppose that this is in a ideal situation where there are no diseases, cells are not going to die, isn't it? So the population increases. Now, third day, this gives us that. This gives us that. This gives us that. I hope you can see that this was the same pattern here. Isn't it? So that thing can grow like that, like a tree. If you start putting things here, you will see that at the bottom there, now you're going to have more drop downs there. Altogether. I'll stop because I don't have space, isn't it? But I think at this time, we have got an idea. So what's going to happen now? If you look at the number of cells here, it's 1, 2, 3, 4, 5, 6, 7, 8. Let's put 8 there. A beautiful number. When you come here, it's 4. A beautiful number. When you come here, it's 2. Another beautiful number. When you come here, it's 1. A special number. Altogether. Now, if we check these numbers carefully, maybe 1 is not obvious, but if you check these numbers going up, I think we expect what here? What do you expect here? What do you expect here? Number 16. Please answer the correct question. I'm saying, what do you expect here? So I'm expecting 16 cells here. Altogether. Now, so once you analyze from 2 onwards, 1 is not obvious, but from 2 onwards, it looks like these numbers are actually 2 to the power n, where n is a whole number, isn't it? Now n belongs to these numbers, the whole numbers. Remember we talked about numbers, whole numbers. So n is a whole number from 0 onward. Then what is this? This is actually the population of the cell after n days, isn't it? So now we can put this thing like this. P of n. Now it's a function of n. And each day, there's only one value of the population. The population is not either 80 or 16, it's 8. So that is a function, isn't it? So now, if you look at that now, we really have what we have called, we remember this, we call this thing exponentiation, isn't it? This is the base, this is the exponent, isn't it? So that's why now, a function which behaves like that, this is an example of an exponential function, where the base is 2. But the base does not need necessarily to be 2, always. It can be any other number. Am I making myself clear? Now, I hope you see also that if you try to make a graph for this function, the graph will tell you actually what's happening to the population. This is 1, 2, 3, 4, 5. Then there is 0. 0 first day, there was only one cell. Day 1, there were 2 cells. Day 0, there was 1. Day 1, there's 2 cells. Day 3, 2, 3, day 2, man, 4. Isn't it? 1, 2, 3, 4. Day 2 there are 4 cells. That is day 2. And so on. What is happening according to the graph? Even if someone comes in there and asks, what is happening to that dot? The dot is going up and up, isn't it? What is it saying to us? We know the population is increasing. Altogether. So an exponential function is a function which is from the left to the right. It's actually increasing. Now notice what I've done here. I've been just considering whole numbers altogether. There is a possibility also that we can consider numbers in between them. In between there. And when we fill up the line, remember, we said we come up with what real numbers, isn't it? And we can actually even continue to the left. We can continue extend this domain to the left and say, talk about -1. Then if I talk about -1, now I'm no longer really like looking at the population of what? Of the cells, isn't it? I'm actually taking that function and then making it a bigger function which includes that population of cells, isn't it? So I'm expanding the domain. Altogether. The function was only given for whole numbers, but now I'm considering other values. I'm expanding the domain. Altogether. So now if I get to half to -1, I'll have this thing as 2 to the power -1, which is actually half, which means somewhere here the value of the function will be there. As I go there to 2, it will be quarter, it will be lower. So as I go to the left, it's decreasing, isn't it? Now, taking that point into account that I can consider the numbers in between there, then I will have values here which fall in the pattern here, which fall in pattern there, which fall in pattern there, and they go this side this way, that way, that way. Then I've got something I can call an exponential function. Then once I get rid of 2, just take any a, I can say I'm talking about the function of x. X now I'm talking about the real numbers, isn't it? Which is equal to a to the power of x. And that's an example of an. And there a, I want a positive number. 0 does not produce 1 does not produce something interesting. So that number must be a number. A must be between 1 and a 0, or a is allowed also to be greater than 1. Why am I not interested in 1? Because 1 is not interesting. 1 to the power, any number is going to be 1. It's a constant, isn't it? I'll be maybe talk about simple things there. Guys, by now you should have a good feel of what is an exponential function. Is that right? Okay. So what is interesting here, which I'll try to squeeze in here on this graph, is can we consider a which is less than 1? Because this a we considered here was actually greater than 1, isn't it? And we saw that the graph is looking like this. But I want to talk more about this graph. maybe, then let me consider a situation where I've got, let's say now y is equals to half to the power n. I'll start with n so that you can see the values easily. Let's suppose I am at minus 2 here, minus 3 there. If I take this minus half, half to power minus 3, what is that number going to be? 8. Good. Good. 8. So which means the value of the function here will be very, very high somewhere there, 8. When I go to 2, what am I going to get? 4, which means it's going to be this 4 there. When I get to 1, it's going to be 2, so it's going to be this 2 there. So now the function now is going to come from this direction. When I get to 1, here, it will be half. So it's going to be somewhere there. When I get to 2, it's going to be quarter. What's happening to the function? Decreasing as we go to the right. So we can do the same consideration. If we look about the values, talk about the values in between. If we think of the values in between these integers, we would be filling up. We'll be filling up there. Filling up there. Filling up there. So what does that say? It says this function, if we take the real numbers, is going to go through 0. Because at 0, what is it going to be? Is a is going to be half to the power 0. But the number divided by to the power 0 is equal to what? Y. N exponential to 0 is what? I don't agree with that. Right. I'm going to tell you something today which you are going to try to help your son understand maths better. Is that right? It's not true to say anything or any number to the power 0 is equal to 1. It's not true. Because 0 to the power 0 is not 1. It's actually some kind of capital nonsense. Are we together? Okay. I'm going to explain later. Let me not waste time now. I'm going to explain later what it means to say a number a not equal to 0 to the power 0 is equal to 1. I'm going to explain what just later. But let's look at this graph first. What is happening to the red graph? It's going down from the left to the right, isn't it? What was the black graph? It's going that way, isn't it? This is going to be called exponential growth. Oh, that spelling is wrong, eh? Growth. Let me take a razor here. What's happening here? Okay. Sorry. Okay. That is growth. Are we together, guys? That is growth. Actually, precisely, is exponential growth. It's exponential growth. That is how it's happening. This other graph, this other one, this is for this one. It's called exponential growth. This one is called decay. All together. This black graph is describing even our own population increase is exponential. The red graph, as it is red and dangerous, it is describing how our natural resources are getting depleted. They're depleted exponentially. Then you'll understand why people are crying about environmental conservation, blah, blah, blah. Because if you don't conserve, one day you are going to be watching yourselves dying of hunger. Because the resources are getting depleted, isn't it? So think of other things which behave exactly like this. which will never increase but go down bit by bit, exponential. But my good example is the issue of of our natural resources and the population growing, growing exponential. This is very interesting. You'll hear politicians talk about these things. Say the population growth is exponential. I don't know whether I checked with them whether they understand what they're talking about, but they're talking about this. But Tonto told them something like this. That's interesting. So now do you see the math from the biology thing? Listen, is it? Yeah. This is not always possible to get an example which will always give you a chance to make math. Like I said the other day, some examples, some maths is just maths for maths, some maths you can apply. Then if it offers itself to use it this way to learn, I will always exploit it, because it cannot exploit me. Okay, good. So now guys, I suppose that everybody now has got a good idea of what is an exponential function, what is exponential growth, and so on. Functions, talking about functions again. Functions and equations are very closely related, because now, if I now talk about this population of cells and say, when is the population going to be 32? What do I have there? I've got an exponential equation. So now I've got to solve for this n and say n is equals to, I don't know what's happening there. Then you solve the equation. But we're going to come back to that. But I want to highlight that every time you think about, you discuss functions, you must be somewhere parallel thinking about the type of equations which come up from those functions. Exponential function will deliver us exponential equations or even inequalities. Linear functions will deliver us linear equations or inequalities. Quadratic will do exactly the same thing altogether. So hold on that. Otherwise, at that point, I think I will say that is enough for the introduction of the exponential function. Then we go maybe to some examples. But what I want to do now, next I will discuss the function closely related to exponential function. Okay, thank you for listening there.